Hi, my name is Matt Q, and today I will be giving you my ISM presentation on multidisciplinary engineering. It's kind of a mouthful, but eventually I'll be able to explain why I chose such a specific name as that instead of like mechanical or electrical engineering. So first I'll start with my quote. Scientific research is human endeavor. The choices of topics that we research are based on our biases, our beliefs, and what we bring. Our cultures and our families. The kinds of problems that people put their talents to solving depends on their values, by Dr. Clifton Poudry. I actually got this quote from a college application, and so after reading that, I just kind of figured it applied pretty generically to engineering. But throughout ISM, I found this quote kind of successively changing meanings for me. At first, I thought this would mean I'm really into music, I'll talk about that later, and so I thought maybe every problem that I would like to solve would be regarding music. But I eventually realized, working with a pediatric therapist, that just more generically, I like to work on any kind of project that I knew would improve any kind of work environment for people. So as generic as it sounds, I realized that I actually like helping improve people's either lives or just simply their workspace. Quick about me, I'm a senior at Frisco High School. I'm very heavily involved in music. I play at my church band, I play in the jazz band, play in the school band, and I'm in percussion, so drumline. And then next year, I will be going to the Massachusetts Institute of Technology, majoring in Course 2. They like to number everything, so Course 2 is mechanical engineering. But if you call it that, no one knows what that means. So during my first semester, I did a lot of less specific research and just more generic research about maybe which engineering discipline I would like to do. And so the first one I looked at was materials science and engineering. And so I was introduced to this field of engineering at a summer camp at the Missouri University of Science and Technology. And down here is actually one of the things that inspired me to look into the field. So what those are those microscopically tiny beads that can be irradiated and shot into a specific area of the body. Right now they use it in the liver. And so they're small enough to pass through veins and arteries, but they get caught in the capillaries. So what essentially is happening is you're having this highly irradiated material concentrated in one area, and that's actually a huge advancement in cancer treatment because normally you can't target a certain organ, but with this they are able to. So that was kind of what inspired me to look into material science. But upon my research, I found out that job opportunities were very limited. The job growth was less than 1%. And it just wasn't looking very good. So I decided that it was probably too narrow of a field to study and that maybe I'd want to branch out and find something broader. So the next one was chemical engineering. Obviously, it's more general than material science. Chemical engineers are often called the generic engineers because they can be employed in just about any field of work. But then I started thinking about something very obvious that maybe I should have thought about before, which is that I didn't like chemistry that much, and I actually like physics way more. And specifically dealing with ISM, I couldn't think of a good way to create a real product that was viable. One of the things I researched was toxicity testing. So if I did anything that had anything to do with chemicals, I would have to go through the tedious task of toxicity testing, and that just to make sure like anything that I created wouldn't give someone cancer, and that would be a lot of work, and I just decided that I wanted to try something else. So mechanical engineering, it's a pretty generic major, and just like chemical engineering, it can be used in just about any field. And so what inspired me to look at this was I visited Bell Helicopter with Austin Schneider. He's an aerospace engineering ISM student. And so something I kind of realized while I was there was that I really liked the design aspect of just engineering in general, and that was most commonly used in mechanical engineering. And then obviously mechanical engineering encompasses a wide variety of other disciplines. So I figured I'm kind of a generalist, so maybe I should try this out. So some of the interviews that I went through, this was just kind of chronological order. So Randall Burrell, he was from Raytheon. He's a mechanical engineer. Sean Coffey, he's a chemical engineer. And so something I found with these two was they were kind of more involved in the management side of engineering. And so just talking to them, it was helpful, but I kind of realized that I, at least as a young engineer, want to spend more time on the design side than management. Chris Wu and some associate engineers I met with, they were the ones at Bell Helicopter that I talked to. Dustin Miles was one of, although he was a materials engineer, he was one of the reasons why I decided to go into mechanical engineering. So his title is a materials engineer at Lockheed Martin, but I actually found out that he's a mechanical engineer, or he got a mechanical engineering degree from UT. And so literally when I asked him how did he get the job in materials engineering, he said he applied for it and he got the job. So I figured if a mechanical engineer can get a job in materials engineering, I can just get a mechanical engineering degree and probably get a job anywhere. And the last interview was Mike Albrecht. He's from AT&T. His formal study was in computer science, but he's now, and I'll talk about this, he's now an innovation coach for the AT&T Foundry. And so just kind of the description here, at the Foundry is kind of a break off from AT&T. So AT&T is obviously a large company. And so the Foundry is supposed to be kind of the startup environment. Basically what they'll do is they meet with business units and they'll kind of ideate or brainstorm for a small period of time. Then after that small period of time, once they've created a financial plan and they know exactly what they're going to produce. As far as a prototype, they begin their 6 to 12 week sprint. And so basically that's when the startup will just work as diligently as they can to finish their product. And so that was kind of perfect for ISM because this is literally what we do in ISM. We have a very short time span to get something incredible done. And so working with Mike was just an obvious choice. So just quickly about my original work. So when I'm talking about, or when you talk about engineering, you always have to find the problem first, right? And then you have to find the solution. So I wanted to find a music-related issue because, as I said before, I'm very heavily invested in music. And so I thought this would be an easy transition from last year I actually did music production. And so now if I just slowly transition to engineering, I could do it through this. So one of the problems is some guitarists want this thing called infinite sustain. So on a violin, they have a bow, and so they can basically sustain the note for as long as they continue bowing the string. But on a guitar, you pluck a string and then it slowly dies out over time. And so basically, I wanted to construct a handheld device that would emulate a bow, but using electromagnetic principles. And so I actually wasn't the first one to think of this. I had originally thought of this because of a product called the eBow, which is literally what I was doing. But this actually worked out well for an original work because I didn't have to come up with the entire product. I could start with a basis and then I could make my own version. So just quickly about how it works, and on final presentation I'll have like all the stuff I did before. Basically, how a mic and a speaker are the same. It's just that a mic takes an input of signal while a speaker can take the output of signal. If you actually wire a microphone correctly, you can use it to output a signal, or if you get a speaker, you can use it to record sound. And so basically what's happening is if you take that idea and think about feedback. So if you've ever talked in front of an audience with a microphone and you step in that awkward spot where the microphone gets that one frequency that starts really whining, basically what's happening is the frequency is going into the microphone that's coming from the speaker, goes through an amplifier, and as you can see, it's just going to get louder and louder. So usually the way you avoid that is you get out of line of the speaker. So what I did was I took these feedback principles and I applied it to how a pickup works. Pickup doesn't work exactly like a microphone. Basically, the only step they do in between is there's a magnet in the pickup, and when the magnet vibrates at a certain frequency because of a metal string, it generates that frequency, and so that's how that works. This is a picture of my original work, kind of the first prototype. This is just a quick circuit schematic. Basically, all you need to know is earlier when I said a speaker and a microphone can work to create feedback, this is the magnetic part of the microphone and magnetic part of the speaker, and so they're going to create feedback to sustain a note. So in my original work, I had about 3 different iterations. So the first prototype was just kind of getting the circuit itself to work. And so I learned about this technique called breadboarding. And so you can actually see the breadboard over here. Breadboarding is a good technique for creating a circuit without actually having to solder the joints. And soldering is just the use of a conductive metal, superheating it so that it melts in between the joints that you want to meld together, basically. And so when it cools, it's conductive so that you can still conduct current through it. And now the joints are connected. And as you can see, the circuit is over here, and then the 2 coils that I talked about are inside a makeshift balsa wood enclosure. And so over here, should I demonstrate the whole thing like I did last time, or should I just have a video? Okay, all right, so I'll do that. And so that's what that is. So the second iteration was kind of moving from the breadboard to a more permanent state. And so over here you can see this is called protoboard. And so obviously now I'll have to use the technique of soldering to connect all the little wires and the components like I did over here. I still stuck with balsa wood because I didn't want to yet make the enclosure. And you can't see it, but there's a battery casing over here. So now with this second iteration, I've made a much more compact version of my bow. And so with the third prototype, and we still haven't gotten to print it because basically we're waiting for deadline. There's like the ink expires, and so when it gets to a certain point, basically they have to use up all the ink, and so when that day comes, we can print this, and so that'll be nice. But through here, I got to use a software called OpenSCAD, and so this is a free software that I can use. I had originally thought I was learning actual like computer science, but I eventually learned that I was just writing in pseudocode. So basically, it's just a simple code that people can learn to write in the specific program. You can't use the language across all platforms to actually use it. It only works within the parameters of this application. But if you can see, I made the entire 3D design of the enclosure. On the bottom you can see the little rails that I can fit on the guitar strings, and then in here is where the protoboard version of the circuit is going to rest, and then the battery on top of that. And so just kind of the significance of my original work. Although I didn't use all of the, more specifically just the 3D printing, a lot of this is kind of what I'm going to be using eventually in my final product. So just in general, working with a circuit and having to design a circuit, which is what I have to do in my final product. Thankfully for the original work, I didn't have to design the circuit. But in addition, this was a small introduction to coding, which I had to learn for my final product, which I'll talk about. And then, obviously, like I just said, this original work provided me a way to learn about the technical aspects of working between computer science and electrical engineering without having to actually design the specifics. So my final product. Just real quick, last year when I did music production, I actually created a 10-song album. And so obviously with that, I got to work with a lot of people. So I kind of wanted to create a similar experience with working with another group of people. Obviously this was more specific because it was only with 2 people. But over here, this is Lauren Bradford. She's an ISM student that is studying pediatric therapy, and this is her mentor, Bonnie Rogers. And so identifying the problem, like I said, when you're in engineering, you want to know what kind of problem you are wanting to solve. And so over here are just kind of some of the ideas that were thrown out when we were ideating what we might want to solve. And so this first one actually wasn't the first thing that we came up with. It's just the one we ended up choosing. But learning to quantify data, or figuring out how to quantify data for any given exercise. So as you can see here, this is a swing that they use in the gym at for the pediatric therapy environment. And so a lot of their exercises are based around these swings. There's a variety of different swings, like a parachute or like a normal swing or like a pogo sticks that moves around. And so something that a lot of parents don't get out of this is they basically see their kid playing. Bonnie knows, or Bonnie and Lauren both know, that when a kid is doing these different exercises, they are actually improving their muscles. But sometimes some parents obviously are skeptical. So when they see their kid just swinging around, they don't assume that nothing's getting done, but they don't feel entirely confident. And so by finding a way to quantify the data, you're able to give the parents physical proof that their child is actually improving and that they're actually getting their money's worth for having their kid go through all these exercises. Just a few other ideas. One of them we thought about was the encouragement for home exercises. So if anyone's ever done physical therapy, you often get exercises that you have to do at home and people don't do them. Surprise. So we were trying to think of a way to come up with something to encourage people to do that at home. And then a third idea was just kind of Bonnie found that there's no standardized test for how kids learn. And so this is obviously, we really wanted to pursue this, but just the implications of it were just massive. Basically what we would have to do is create a standardized test that would output a score and tell you if your kid was a visual learner, if he was an active learner, if they were just an observational learner, tactile, or just kind of audio. And so that, I mean, obviously as a teacher you understand the implications of creating a test like that would be like massive, and so we knew we couldn't really pursue that. Next step for once we identified our problem was kind of creating the solution. So in creating our final product, obviously working between two students, we kind of had two working products. And so this first one is kind of Lauren's side of what we were doing. And so basically when we were talking with Bonnie, the first thing I actually asked her was, is there a piece of equipment that you feel like you don't have that would benefit your patients? And so I asked that not thinking I would get a really solid answer. I thought maybe they basically had everything, and almost instantly she said one of the problems she has is that right now they have a tunnel that kids can go through, and the middle of it is composed of stretchy material, so that when a kid crawls through the tunnel, the material actually encloses around them. And so it might not sound very difficult, but for kids that have underdeveloped muscles, it actually is a very crucial exercise. And so the problem that Bonnie found was that she had the tunnel, which was great, but she wanted to be able to suspend it in the air like she had with all the other swings. And that would kind of add another dimension of difficulty, just kind of making things more difficult muscularly for the patients so that they could develop even more, not just muscles, but awareness of their surroundings. And so when we wanted to develop this suspended tunnel, as we called it, we quickly realized that there was a legality issue. So in creating any kind of pediatric piece of equipment, it has to go through manufacturing regulations, and it has to be like physically proven that it can support any whatever weight range of child that you say it can support. And so we didn't want to have to deal with all those legal issues. So basically the way we got around it, and I'll go back, is we used this swing over here to start as the base, because we knew obviously that it was authorized. And in the gym all the time they always add different things, like maybe this pillow back here they'll add to an exercise to make it more difficult. And obviously this pillow isn't like regulated or FDA approved because it's just a pillow. So we figured if we can make the tunnel itself and just place it on that platform, then we would be able to achieve what Bonnie wanted and not have to work around all those legal issues. And so down here you can see me inside of the initial prototype. The next step for us is to wrap that prototype in marine vinyl material, which is what the standard is for the material in the gym, because obviously in an environment where kids might be sweating or just like in general getting moist, you need material that can withstand that. And so we'll be wrapping that, and then on the inside we'll be using a similar stretching material that I described for the tunnel and placing it on the top so that it can droop down and enclose around the child. And so before we went on to creating the device that I was going to do for my final product, we had to talk a lot about how are we going to present this data that we get from the device. And so one of the things we first talked about was a score. And so basically whatever device I would create that would quantify the data, it would take it, do whatever calculations that we needed to do, and it would output a score. But I had an interesting conversation that I didn't realize about pediatric therapists, is that they are not legally allowed to give a diagnosis because they are not actual doctors, right? So even though a score might be harmless, you're not telling a kid that they have a cerebral palsy or anything. You are giving a score that has a standard, and if they're performing poorly, then you're telling the kid that they are doing something poorly. And so really, even though we wouldn't want to imply anything like that, it's just not allowed because we're taking data. All that Bonnie can do with that data is kind of guide the student through exercises based on what she can do, but she can't look at the data and tell a kid that they are lacking in this skill or looking at another skill. So basically what we decided was to give the most objective presentation of the data. We would just put it in a graphical format. And so I'll talk in a second. Two of the main pieces of data that Bonnie wanted to find were sway, which obviously in a swing setting you're going to be moving side to side. And so sway is just the physical degree that it's moving side to side. And so just in general, when a kid is in exercise, you always want the swing to be as still as possible. So if your sway is high, then you're moving around a lot, which means your success rate is a lot lower. And so just by showing a graph of how far from an equilibrium point that a kid is moving, they can very easily see how they're doing. And so instead of outputting a score and telling the kid you need to work better on this or your sway is too high, then they can just see it themselves and realize that they need to improve without telling them. And so the other aspect of the graphical presentation is that over time we'll have this kind of storage of graphs, and the idea is that this goes back to the quantifying of data. If you can see the graph and you can see the physical line of how much they are moving from the equilibrium point decreasing over time, then the parents can actually physically see that, okay, my child is improving in this exercise, so they must be getting something out of their money. And so my side, that was what I just talked about, was kind of Lauren's side of the final product, and now this side was kind of more of the engineering side. And so this is the device for quantification. So earlier I talked about sway and thrashing is the second piece of data that Bonnie wanted to identify. And so the first one, sway, like I just talked about, there are a variety of ways to go about finding how far from a center point the swing is moving. And so the first one that we talked about is an accelerometer. Basically, what an accelerometer is, it can detect on a three-dimensional axis the different amounts of force that the sensor is experiencing. And so for those of you that haven't been in physics for a long time, you know that the force of gravitation of the Earth is always constant. And so basically, if I'm holding an accelerometer flat, the X and Y directions should be 0 because they're not experiencing any force when it's still, but the Z direction should be equal to the force of gravitation of the Earth. And so basically, what you can tell is when you rotate that, then that force of gravitation is still coming at this angle, but now it's influencing the different axes. And so you can use that information to find the orientation of the accelerometer. And using some single variable calculus, you can actually find from a starting point, how like the exact position of a certain object. But Mike was kind of like, you don't have much experience in computer science, so I wouldn't want to add in calculus. Even though I'm aware of how that works, I just wouldn't want to add in calculus to computer science, which I'm already pretty inexperienced in. So the next kind of sensor that we talked about was an ultrasonic sensor. And basically, it operates off of similar principles that radar might use. If you imagine, I have my sensor and I'm shooting a audio signal to the wall, obviously a high frequency signal so that you can't hear it, and then it bounces back, then the sensor can tell how far a certain object is from it. And so the idea would be that if we set up the sensor to the side of the swing, then we would be able to know exactly where the position was. But Mike kind of discouraged using the ultrasonic sensor just because its accuracy would be a lot less, and setting the interval of measurement would be kind of difficult because you can't have a constant signal going. You have to send out one signal at a time. And so in that time, you might, it'll be a lot less accurate because you might not send out a signal when the swing is at its maximum swinging point. So the third kind of sensor that we decided to go with was the magnetometer. And so basically, the magnetometer works very similarly to an accelerometer. It's, instead of detecting force, it detects magnetic force. And so I should probably get like a diagram next time so people can see. But basically, if I have a magnet and I'm moving it closer, the magnetic field near that sensor is going to increase. And so using one of Maxwell's equations from integrated physics, I can actually find out the distance that the magnet is from the sensor because of the relationship between distance and magnetic field strength. And so basically what I was able to do with that was it was the most accurate sensor that I could use without having to go deep into calculus and all that stuff. And so by knowing how far that the swing is from the sensor, I can do just simple trigonometry to find the angle of the swing, or I can just know that the swing is passing a certain threshold that I'll talk about down here. And so the second piece of data that Bonnie was talking about was just thrashing in general. So obviously on the swing itself, you have side-to-side sway, but you also want to know how much the kid is actually struggling inside of the swing. And so using the accelerometer that I just talked about above, I can actually create a wearable. So you see a lot of those Fitbits or like kind of bracelet looking things. And by putting the accelerometer on the child itself, you can see how much in general they're moving around. So using the idea that the accelerometer can detect force, if the kid is thrashing around a lot, the overall vector of their acceleration or force that the sensor would be experiencing will increase. So just by graphing that in general, you can see that as the force in general increases, the amount of thrashing is increasing. And that actually goes back to the graphical presentation that I just talked about, where the parents can see that at first their child might be thrashing around at this amount, and then so over time they should be able to see that the thrashing is decreasing as the child is able to control themselves a lot more. And the third part was adding a kind of feedback for the child during the exercise. So we wanted to create some audio-visual cues. So the first idea was a stoplight kind of visual cue. So basically for the child to see a green, yellow, and red light, when they're still, they'll be on the green, and when they start to sway at a certain degree past a certain threshold, then the light will turn yellow. And once they go to a even farther threshold, then the light will go to a red. And so we really liked that idea just because it kind of fits in with the playful environment that the gym likes to foster. But we also realized that although this was a nice idea, the kid is focusing on an exercise, and for them to be able to see a light the only way we could have done that was if we turned off the lights in the gym and had massive lights like blasting the color, so that no matter what angle or what they were doing or where they were, if they're inside a tunnel, they would be able to see the color.